Welcome to Basic Mathematical Analysis class. Today we will discuss about Archimedean property. Archimedean property. Let us see what you mean by Archimedean property. This is refer to your textbook number 2.4.3. Archimedean property. It says that if a real number is given, we can find a natural number which is greater than that given real number. True, right? Whenever you are giving some 100 or 100 by 100 pi, suppose you are having 100 pi, then can you find a number which is greater than this 100 pi? Evidently, right? Because you can take 1000. 1000 is not going to be, sorry, greater than 1000, right? So this is a natural number and this one is a real number. So whenever you are having a real number, you can go for a natural number which is greater than the given real number. So statement, if x belongs to R, then there exists some nx belongs to n such that x is less than or equal to nx. So this is the statement. If a real number is given, we can find a natural number such that the real number is less than that natural number. So how to prove it? How to prove this result? We will prove this by proof by contradiction. That means we will first assume that such a number does not exist. Then we will arrive at some absurdity or contradictions. So suppose not. Suppose that is, there does not exist some number nx belongs to n such that your x value is less than or equal to nx. X value is less than or equal to nx, which implies your n is less than or equal to x. Am I right? You cannot find any natural number which is greater than this x. That means all the natural numbers are less than or equal to x for all n belongs to n, right? For all n belongs to the natural number. That means your natural number is bounded above, which implies x is an upper bound. X is an upper bound of n. Okay, otherwise your set of natural number is bounded, that we can say bounded above. Okay, then by completeness property, the set is non-empty and has a upper bound. That means it has got a supremum. Okay, that means the set of natural numbers have a supremum. Then by the completeness property, then by the completeness property, the non-empty set n, has a supremum, U belongs to R. Just got a supremum, U belongs to R. Then U minus 1 is less than U. Since U is the supremum, U minus 1 should be always less than U, which implies U minus 1 is not an upper bound. Which implies U minus 1 is not an upper bound of N. Can you follow? Supremum means it should be the least upper bound. So here we have assumed U is the supremum, and if you are taking a number less than U, that cannot be above upper bound. So U minus 1 is not an upper bound of N, which implies, what's the meaning of this? This meaning is that there exists some number, a natural number, which is greater than this U minus 1, right? Which implies there exists some natural number such that this U minus 1 is less than this M. This number is greater than U minus 1, since U minus 1 is not an upper bound. So this implies, from this you will get U is less than M plus 1, right? We know that M belongs to N, and therefore M plus 1 also belongs to N, right? M is a natural number, then M plus 1 is also a natural number. Now what you got? U is less than a natural number. What was your U? U was the supremum of N. This is a contradiction, right? So which is a contradiction? Which is a contradiction since U is the supremum. U is the supremum, which implies our assumption is wrong, right? Our assumption is wrong. What we assumed? We assumed that such a number does not exist. Therefore, for x belongs to R, that is whenever x is the real number, there exists a natural number nx belongs to N such that x is less than or equal to nx. Hence the Archimedean property. Hope you understood. Next one, we will have three corollary of this theorem. Corollary 2.4.4 corollary. If S equal to set of all 1 by n such that n belongs to n, then infimum of S equal to 0. This I have given you as a homework. Are you remembering? To find the supremum and infimum of this set. Now we will prove that. Just I ask you to find. Now we will show that infimum of this set is 0. Proof. Since this S not equal to empty is bounded below by below by 0, right? Now it has an infimum. Then it has an infimum. And let W is equal to infimum of the set S. Now if W is an infimum and we have found that 0 is a lower bound, so your infimum value should be always greater than or equal to 0. Then your infimum value, that is W, is always greater than or equal to 0. Now let epsilon greater than 0 be given. Then by Archimedean property, Archimedean property, what you will have? There exists some n belongs to n such that your epsilon is less than this n. For that I can put epsilon greater than 0 means 1 by epsilon also result real number. So 1 by epsilon I am taking. 1 by epsilon is less than n because 1 by n is also a real number. Then by Archimedean property, whenever you took a real number, you can find a natural number which is greater than this real number. So this implies from this you will get 1 by n is less than epsilon, right? 1 by n is less than epsilon. Therefore we get, first we are having 0. 0 is less than or equal to W, that we have. Now this value is less than or equal to 1 by n, and this value is less than epsilon, right? Because W is the infimum, 1 by n is a member in your set S, so W should be always less than or equal to 1 by n. Now we are having the Archimedean property for this 1 by n, and this 1 by n value should be less than epsilon. Now we are having W is less than epsilon. Now we have studied that whenever you take an arbitrary positive element epsilon, and then you are getting a quantity A is always less than or equal to epsilon, implies that A is equal to 0. Okay. Since epsilon is arbitrary, it follows from theorem 2.1.9. What was 2.1.9? 2.1.9 says that if epsilon greater than 0, then A is less than or equal to epsilon for every epsilon, right? Then A is equal to 0, right? Then by theorem 2.1.9, we get, here we have got W is less than or equal to 0. Sorry, W is less than epsilon we are getting. So we get your W value is equal to 0. Now what was our W? We have assumed that W is the infimum of the set, right? Yeah, infimum of the set S. Therefore, infimum of S is equal to 0. This is the first corollary. It's easy, right? Now we are going for the next corollary, that is 2.5. 4.5 corollary. The very simple one. If t greater than 0, there exists xt or nt, right? Nt belongs to n such that this is nt, right? Not xt. Nt there exists nt belongs to n such that 0 less than 1 by n less than t. What's the meaning of this? We can have nt here also, nt, right? So if t is greater than 0, then we can find a natural number which is whose reciprocal is less than that t. Can you follow? I repeat, if t is a positive real number, then we can find a natural number whose reciprocal is less than the real value. Okay, so how to prove it? Again, we should take the set S, right? So proof, since infimum of 1 by n, comma, n belongs to n is equal to 0, and given t greater than 0. Since infimum of 1 by n, n belongs to n equal to 0, and given t greater than 0, then t is not a lower bound of a lower bound of the set S equal to set of all 1 by n, n belongs to n. Set of all 1 by n, n belongs to n. Okay, first you are taking infimum of this set is 0, that we know, and given t greater than 0. Then t is not a lower bound, right? T is greater than 0. Now t is not a lower bound of the set S, which implies, what's the meaning of that? It is not a lower bound means there is having element which is then t, right? So there exists some natural number nt belongs to n such that the member, which should be the member 0 less than the member in the set is 1 by nt, and this value is less than t. Since t is not a lower bound, there is an element which is less than t, so that element is 1 by nt. So we want to prove this thing only, less than t there exists a 1 by nt, right? So we have got the proof. So hence the corollary. Now we will pass to the next corollary, 2.4.6 corollary. 2.4.6 corollary. If y greater than 0, there exists exist ny which belongs to oh sorry ny belongs to n such that ny minus 1 is less than or equal to y, it is less than ny. Okay, that means if you are having a real number greater than 0, then we can find natural number such that natural numbers minus 1, this y will lies in between the natural number minus 1 and the natural number. For example, if you are taking 7.5, it's a real number, right? Now can you find two natural numbers? Of course 7 and 8 is there, so in between only 7.5. okay, so like that, if you are having any real number, you can find two natural numbers such that this real number is lying in between these two natural numbers. Lying between does not imply that exactly half of that, right? Okay, somewhere, because when you're taking here 7.3, then also 7 and 8 is valid, right? Even 6 and 8 is valid, 6 and 9 is valid, everything is valid, right? So how to prove this one? Proof: consider the subset, consider the subset ey. Ey is equal to set of all m belongs to n such that y is less than m of n. We are taking a subset of the natural number, that is set of all m belongs to n such that y value is less than m, right? That means if you are defining e1 means we want to have those y value those number which are greater than this y, okay, natural numbers. So greater than means I will get e1 equal to 2, set 2, 3, 4, 5, etc. This is my e1. Similarly, e2 means I will get 3, 4, 5, etc. like that. Okay, so this is my set ey. Now this is non-empty, right? Which is non-empty. Then by Archimedean property, Archimedean property, which is non-empty by Archimedean property, right? So whenever you are having a real number, there should exist natural number greater than 1. So which is non-empty by Archimedean property, that we can say. Next we are having by the well-ordering property. Then by the well-ordering property. What is my well-ordering property? Well-ordering property is this: every non-empty subset of n has a least element. Has a least element. So this is the well ordering property. Every non-empty subset of natural number has a least element. For example, if you take E1 subset of n, right? 2 is the least element. This 3 is the least element, right? It's like that. It's the least element. So what do you follows? Which implies, oh, we are written then by the well-ordered property, right? There's no need of implies. Then close the bracket and write. Then by the well-ordered property, EY has a least element, right? EY has a least element. Ly has a least element. Say I am denoting it as n suffix y. Okay. Then it is the least element. Then ny minus 1 does not belongs to EY, right? Take E2. Now E2, 3 is the least element. Okay. Then 3 minus 1, 2. 2 does not belongs to EY, right? Like that, ny minus 1 does not belongs to EY. N suffix y, confusion in writing. Okay. N suffix y minus 1. Okay. It does not belongs to EY. Hence, we get, what do we get? Ny does not belongs to EY. That means ny minus 1 is less than y, right? Am I right? Thus we get ny minus 1 is less than y, which is less than or equal to, so you can put ny. True? Strictly less than ny. Okay. Now what you got? See, proof of this is, first we have considered the set EY. EY is set of all m such that y is less than m. Okay. So E1 means this, E2 means this, etc. Then by the well-ordering property, that means every non-empty subset of natural numbers has the least element. Then E1, E2, etc. EY should also have a minimum element. I'm taking that minimum element as ny. So ny is a minimum element, means ny belongs to EY, right? So ny is an element in EY. Now if I am taking ny minus 1, it is not an element of EY. So the meaning is that by definition of EY, one element is not a member means this member should be less than y. Okay, so ny minus 1 is less than y. Already ny is the minimum, right? So this value should be, or this ny belongs to y, ny belongs to ey, then y value should be always less than ny, hence the corollary. So today we have seen the Archimedean property and its three corollaries. Okay, so this is going to be a very easy one, just you go through it. If you're finding any difficulty, please let me inform it, then we can go for the corrective measure. Okay, so I'm winding up today's session here. Thank you for your patient listening. Thank you.